Hello everyone, my name is Kaatyaayan Kashyap Saikia, MEB 19034, and today, along with Shivam Parashar, MEB 19031, we are going to discuss some of the basic applications of the second law of thermodynamics. So now, second law of thermodynamics. The first law of thermodynamics simply says that energy is conserved. It does not give any direction for a particular process. It is the second law of thermodynamics which gives direction for a particular process through the concept of entropy, and so it is also known as the direction law. There are two statements of the second law of thermodynamics. The first statement is the Kelvin-Planck, which states that it is impossible for any device or to develop device that operates in a cycle to receive heat from a single reservoir and produce a net amount of work. The second statement is the Clausius statement, which states that it is impossible to transfer heat from lower temperature to higher temperature without any external input. Applications of second law of thermodynamics, day-to-day life. The first application, refrigerator. As shown in the figure, we can see that there is the heat movement from cold region to hot region. The refrigerator basically works on the concept of maintaining lower temperature in comparison to surroundings. A refrigerator causes heat to flow from cool to hot by inputting work which cools the space inside the refrigerator. It is an open system that dispels heat from a closed space to a warmer area, usually a kitchen or another room. By dispelling the heat from this area, it decreases in temperature, allowing food and other items to remain at a cool temperature. It is a work-consuming device. Working of refrigerator. Work is inputted which compresses a coolant, increasing its temperature above the room's temperature. Heat flows from this coolant to the air in the room, reducing the temperature of the coolant. The coolant expands and it cools down below the temperature inside the refrigerator. Heat flows from the refrigerator to the coolant, decreasing the temperature inside. The process which is seen here is cyclical, and this allows the refrigerators to be run for as long as necessary. The work input equation is given by QH minus QC, where QH is the heat given out to the room and QC is the heat taken out. The coefficient of performance of refrigerator is the ratio between QC and QH minus QC, or we can say that COPR is equal to QC divided by QH minus QC. From the above work input equation, which is QH minus QC is equal to work input, this equation shows that a refrigerator must exhaust more heat to the room than it removes from the inside, and also if the COP value is high, it is better because less work is being done to cool down refrigerator. So now coming to the heat pump, it is a device that transfers heat from low temperature medium to a high temperature medium. It absorbs heat from a low temperature source and then gives this particular heat to a warmer medium. There are two sources or two reservoirs, cold reservoir and hot reservoir. In the diagram shown in the side, there is this particular anti-clockwise direction arrow. This arrow pertains to the meaning that it is a work consuming device. The work input equation is QH minus QL, and this gives the explanation regarding the work input. The work is what we pay for, and the outcome is seen in the heat generation or movement from cool to hot reservoir. The COP of heat pump is QH divided by QH minus QL, where QH is the desired effect of heat pump. The heat pump is actually the heat engine running in reverse. Energy W in is injected energy is extracted from the cold reservoir, energy is transferred to the hot reservoir. The above given points why heat engine running in reverse is heat pump can be illustrated as shown in the figure. So this was all about heat pump. Now coming to the performance of refrigerators and heat pumps. This term can be expressed in terms of the coefficient of performance COP, which is defined as the ratio of desired output to required input. The COP of refrigerator is cooling effect by work input, which is equal to QC by net input work, and COP of heat pump is heating effect by work input, which is QH by net input work. Here QH can be replaced by the equation net input work plus QL. This is the another equation for QH, and also QC can be replaced by QL. So COP of heat pump comes out as net input work plus QL divided by QH minus QL. So this can be also written as net input work divided by QH minus QL plus QL divided by QH minus QL. This whole part upon simplification gives out as comes out as 1 plus COP of R. COP of heat pump is equal to 1 plus COP of R. This is the relation between the coefficient of performance of heat pump and refrigerator. Now coming to the last part, heat engine. It is a device which converts part of heat into work and rejects remaining to sink and surrounding. The concept was given by Calvin Planck's statement, which said that complete conversion is not possible, but partial conversion is possible with the help of two thermal reservoirs, source and sink. There is this hot reservoir and cold reservoir. These are the two reservoirs upon which the working is based. This particular arrow denotes that it is a work producing device. There is net work production, QH movement from hot reservoir to heat engine, QL is net movement from heat engine to cold reservoir. A heat engine typically uses energy provided in the form of heat to do work and then exhausts the heat which cannot be used to do work. As shown here, all real heat engines lose some heat to the environment. The efficiency is W by QH is equal to QH minus QC divided by QH. A pressure versus volume graph is also shown. From point 1 to 2, there is heat addition. From point 2 to 3, there is work done by gas. From point 3 to 4, there is heat extraction. From point 4 to 1, there is work done on gas. The first law and second law of thermodynamics constrain the operation of a heat engine. The first law is the application of conservation of energy to the system, and the second sets limit on the possible efficiency of the machine and determines the direction of energy flow. So this was all about the certain applications of the concepts related to second law of thermodynamics. So with this, my part gets concluded, and the next part will be explained to you all by my group work partner. Thank you.